So we move on to derivatives, and derivative of a function y equals f of x is denoted by dy over dx, or y prime, or f prime of x. It is a matter of choice as to which you want to use. But if we go to higher order derivatives, it is best to stick with the prime notation because it is quite compact. Now, what would the derivative equal to? The derivative of a function is equal to the slope of the tangent line at a given point. We've got to be careful here because later on we will see that the derivative of a function is a function in and of itself. In other words, for every single point of the function, we could find the derivative of the function. So, as of now, I'm only talking about one single point. Now, how do we find the derivative? The derivative is directly related to the difference quotient. So, we know we recall the difference quotient is f of x plus h minus f of x divided by h. So the derivative f prime of x is simply the limit h approaching 0, f of x plus h minus f of x divided by h. So the limit h approaches 0 of the difference quotient is the same as the derivative of the function at some point x. So now that we know what a derivative is, the next question is, should we use the difference quotient each and every time to find the derivative? Now in the next video, maybe this one and the next one, I'm simply going to use the difference quotient to find the derivative. But in practice though, that is not effective. You know, it is going to take a lot of time to make use of the difference quotient to find the derivative each and every time. And that's where we have rules of differentiation come into play. So the slope of the tangent line at a point x at some point x is the same as the derivative of the function at some point x, and that is denoted by f prime of x, and we could also denote it as dy over dx or y prime. Again, it is a matter of choice. Now, derivatives do fail. Derivatives are feasible only for continuous functions. feasible at that removable discontinuity. And there are certain cases where the function might appear continuous, but a derivative may not be feasible. For example, take this absolute primary function. Let's just say we would not have a derivative. The reason being it is a sharp curve. And the last case, that function looks pretty continuous to me, but as x is equal to 2, there is no derivative, because it is a constant. So we've got to know when a derivative will exist. So typically, as a golden rule of thumb, if you have a continuous function, then we don't have a problem. We will have a derivative. Everything is peachy. But if there are discontinuities, then the point where we have a discontinuity will not have a derivative. This goes back to limits. If we have limits and if there are discontinuities, a limit doesn't exist at the discontinuity because the right-sided limit will not match the left-sided limit. So a good example would be the jump here. If I say that that is 1 and that is 2, the right-sided limit toward 2 is 2, and the left-sided limit is 1. And they don't match. If the limits don't match, if the one-sided limits don't match, then the limit doesn't exist. And if the limit doesn't exist, then the derivative cannot exist. The reason being the derivative is directly related to the limit at a given point. So discontinuities are quite important when we try to find the derivative of a function. So how do we find the derivative of f of x is equal to 3x minus 8? 3x minus 8 is a line, so it is of the form mx plus b, and we know the slope of a line is simply m, and in this problem it is 3. So if we have a line, so the y-intercept here is negative 8, we'll arbitrarily say that that is y equals 3x minus 8. No matter what point I pick on this line, the slope will be the same. So if I drew a tangent line here, no matter what point I pick, the slope is going to be the same. So slope of the tangent line would simply be 3. So which is negative infinity to infinity. So, in other words, the derivative is 3 for every point in negative infinity to infinity. That is the domain of the derivative also. Now, how do we verify this? We know the derivative f prime of x is simply limit h approaches 0, f of x plus h minus f of x divided by h. So, limit h approaches 0. The function is 3x minus 8. So I'm going to replace x by x plus h minus 8 minus the function 3x minus 8 divided by h. So if I distribute, I would have 3x plus 3h minus 8 minus 3x minus 8 divided by h. I'm going to move things around here so things become clear. I'm going to write this as 3x minus 8 plus 3h minus 3x minus 8. That term and that term are one and the same, so they will get cancelled. And we have limit h approaches 0, 3h over h. The h's go away, and limit h approaches 0, we get 3. And there is no h in that limit, so the answer would simply be 3. So as I suggested at the very beginning of this problem, that the limit of this the derivative of this function would be 3 in the domain of the function. And it turns out that f prime of x, which is the derivative, is 3, no matter what value of x I pick in negative infinity to positive infinity. So the derivative is 3. So what we're trying to say here is the slope of the tangent line at any given point on this function is 3. So the derivative is 3. The slope of the tangent line at any point of this function is 3. So the derivative of this function, 3x minus 8, at every point in the domain of the function 3x minus 8 is 3. Now here is another example where we have f of t equals 1 over square root of t. So first thing we have to do is the domain of f of t. We cannot plug in 0. If we plug in 0, the denominator would become 0, and 1 over 0 is undefined, so the domain has to be negative infinity to 0, union 0 to infinity. So this is an infinite discontinuity at x is equal, t equals 0. Damn it. At t equals 0. Let's find the derivative f prime of t. Now you've got to keep in mind, when we take the derivative, we always take the derivative of the function f with respect to its independent variable. So that is the derivative of f of t with respect to t. And what is t here? T is the independent variable. So how do we find this? We're going to make use of the difference quotient, f of t plus h minus f of t divided by h. So limit h approaches 0, f of t plus h is simply 1 over square root of t plus h minus 1 over square root of t divided by h. So we need to get a common denominator so we can combine the numerators together. So the common denominator is square root of t times square root of t plus h. So I'm going to multiply and divide by square root of t there. I'm going to multiply and divide by square root of t plus h there. And divide the entire thing by h. So we have a common denominator, so we can combine the numerators and write it as square root of t minus square root of t plus h divided by square root of t times square root of t plus h over h. Now if we flip and multiply, we end up having square root of t minus square root of t plus h divided by h times square root of t times square root of t plus h. And you can't simply apply the limit here, because if we did, we're going to get 0 over 0. And this is where rationalizing the numerator comes into play. So limit h approaches 0, I'm going to multiply and divide by the conjugate of the numerator. And I'm going to combine the two roots. And the numerator, if we FOIL, would end up becoming square root of t squared minus square root of t plus h squared. And we divide that by h times square root of t times t plus h times square root of t plus square root of t plus h. The root and the square will get cancelled, and we would simply have t minus t plus h divided by h times square root of t times t plus h multiplied by square root of t plus square root of t plus h. Distribute the negative, we have t minus h divided by h times square root of t times t plus h times square root of t plus square root of t plus h. So the t's will get cancelled. We'll have limit h approaches 0, negative h over h times square root of t times t plus h times square root of t plus square root of t plus h. The h's will go away. We'll simply have limit h approaches 0, 1 over square root of t times t plus h times square root of t plus square root of t plus h. And there is a negative in the numerator. When I apply the limit, I have negative 1 over square root of t times t plus 0 times square root of t plus square root of t plus 0, which is negative 1 divided by square root of t times t multiplied by square root of t plus square root of t. That would equal to negative 1 divided by square root of t squared times 2 square root of t. So that would be minus 1 divided by t times 2 root t. So the answer is negative 1 divided by 2 times t root t. We could also write this as negative 1 divided by 2 t times t raised 1 over 2, and we can combine the exponents and write it that way. And the domain here, since the function has a discontinuity at t equals 0, the derivative will also have a discontinuity at t equals 0. In other words, we cannot plug in 0, in the derivative, because if we plug in a 0 here in the denominator, it is going to result in a divide by 0. So the domain of the derivative is also negative infinity to 0 union 0 to infinity. So here is another function, and we want to find the derivative of this function. So the domain here is negative infinity to positive infinity. The reason being, I can plug in any number in the denominator or the numerator, and I'm going to get a well-defined real number. So how do we find the derivative of x? The derivative, or f of x, is simply df over dx. That is the same as saying dy over dx if I call y is equal to f of x. And that is equal to the limit of h approaches 0, f of x plus h minus f of x divided by h. So in our case, that would be x plus h divided by x plus h squared plus 2 minus x over x squared plus 2 divided by h. And we need a common denominator, just like we required that in the previous problem. So I'm going to multiply the first fraction by x squared plus 2 and divide, and multiply and divide the second fraction by x plus h squared plus 2 and divide the entire thing by h. So you can see why using the difference quotient could get really troublesome anytime we want to find the derivative. Things are getting really complicated here. So we have x plus h squared times x squared plus 2. And the numerator is x plus h times x squared plus 2 minus x times x plus h squared plus 2. I am going to expand and simplify. So I have x cubed plus 2x plus x squared h plus 2h minus x times expand x plus h squared, FOIL, I'll get x squared plus 2xh plus h squared, and I have a 2. And divide the entire thing by h times x plus h squared plus 2 times x squared plus 2. Distribute the x in the second term. We have x cubed plus 2x plus x squared h plus 2h minus x cubed minus 2xh minus xh squared minus 2x divided by h times x plus h squared plus 2 times x squared plus 2. the x cubes will go away, the 2x will go away, and I simply have x squared h plus 2h minus 2xh minus xh squared divided by h times x plus h squared plus 2 times x squared plus 2. There is a h in common in the numerator, so let me switch colors here so you can see things better. H approaches 0. Pull the h out, I have x squared plus 2 minus 2x minus x h, and divide that by h times x plus h squared plus 2 times x squared plus 2. The h's would go away. Limit h approaches 0. We have x squared plus 2 minus 2x minus xh divided by x plus h squared plus 2 times x squared plus 2. If we apply the limit, the numerator would simply be x squared plus 2 minus 2x plus 0 divided by x squared plus 2 times x squared plus 2. So the derivative here is x squared minus 2x plus 2 divided by x squared plus 2 squared. And this derivative would exist on the entire domain of the function because there aren't any discontinuities. So that is how we find the derivative here. Off to the next problem. Here we want to find the derivative of g of t with respect to the independent variable, which is t. So dg over dt, or g prime of t. And in this problem, the domain cannot include the value 3, because if I put 3 in that function, the denominator would be equal to 0. We will have an infinite discontinuity. So I'll make note of that in a second. So limit of the difference quotient, and the domain of the function is negative infinity up to 3 union 3 to infinity. There is an infinite discontinuity at t equals 3. So we have limit t approaches 0, 1 minus 2 times t plus h divided by 3 minus t plus h minus 1 minus 2t divided by 3 minus t, entire thing divided by h. We need a common denominator. So I'm going to multiply and divide the first fraction by 3 minus t. And I'm going to multiply and divide the second fraction by 3 minus t plus h. And divide the entire thing by h. We have a common denominator, so we can combine the numerators. So we have 1 minus 2 times t plus h times 3 minus t minus 1 minus 2t times 3 minus t plus h divided by the common denominator, which is 3 minus t plus h times 3 minus t, and the entire thing will be divided by h. So if we flip and multiply, that would reduce to limit t approaches 0, 1 minus 2 times t plus h times 3 minus t minus 1 minus 2t times 3 minus t plus h divided by h times 3 minus t plus h times 3 minus t. Distribute and simplify. Oh, I made a mistake. It is not t approaches 0. I am sorry. It has to be h approaches 0. It was not blatant. I didn't think twice there. So let's FOIL this. So we have 3 minus t minus 2 times t plus h times 3 minus t minus 1 minus 2t times 3 plus 1 minus 2t times t plus h divided by h times 3 minus t plus h times 3 minus t. So that would equal to limit h approaches 0, 3 minus t minus 2t, minus 2, I'm going to FOIL those two. I'll have 3t plus 3h minus t squared minus th minus 3 plus 6t plus t plus h minus 2t squared minus 2th divided by h times 3 minus t plus h times 3 minus t. You can see how complicated this is becoming. Should have used smaller fonts, I guess. So the numerator would become 3 minus t minus 6t minus 6h minus or plus 2t squared plus 2th minus 3 plus 6t plus t plus h minus 2t squared minus 2th divided by the entire thing, h 3 minus t plus h times 3 minus t. So the 3's will get cancelled, the 6t's would get cancelled, the t would get cancelled, the 2th would get cancelled, the 2t squared would get cancelled, and we are simply left with limit h approaches 0, negative 6h plus h, that's negative 5h, over h times 3 minus t plus h times 3 minus t. The h's would go away, and if we apply the limit, the answer would be negative 5 divided by 3 divided by 3 minus t squared. Since the function has a discontinuity at t equals to 3, the derivative would also have a discontinuity at t equals 3. So the derivative has the domain negative infinity to 3 union 3 to infinity. So we can see how using the difference quotient to find the derivative could get out of hand really fast. So we have to find better ways, and eventually when we get to chapter 3 we'll see that things could get simpler by using rules of differentiation. But the key to remember here is the derivative of a function would be equal to the slope of the tangent line at every single point of the function. And if there is a discontinuity, then the derivative cannot exist at that discontinuity. Also, if there is a sharp turn or a cusp of that sort, the derivative will not exist at that particular point.